Sadly, I've gotten to the point where it's difficult for me to stand for long periods of time, and also difficult for me to walk around. And I'm hoping that I'm going to get some relief fairly soon from that, but we'll see what happens. Um, I have a doctor's appointment tomorrow, and I have to, and hopefully they'll give me some advice and maybe some things that will help with this. Um, so what we're scheduled to do today is the heat of vaporization of water, which in many ways is probably one of the best labs that we can do remotely, because the actual procedure is involved, but also involves quite a bit of sitting. And you just build the thing and then you let it go and you watch it and you collect the data. It's not the most exciting thing in the world. A lot of the other labs are much more involved, so that's good. I wish that we could still do it live, but that's the way it goes. All right. So what I want to do first of all is talk about some of the background of the lab, and then once I've done that, I will send each of you individually a set of data. All right. Now, what you can do is you can go on to Canvas and download a spreadsheet that's titled Clausius.xls, and you can put your data into there, and it probably will work. You'll have your data will come as a PDF file, and I think if you use the right software, I mean, if you were to open it in Chrome or in Acrobat, you could actually just copy the data direct from there and then paste it into the Excel file. I think that'll work. You may have to do it column by column, but you can, it'll save you some time having to type things. All right. So what I want to do first is I want to talk about the background of this lab. All right. If you look at the lab, it says the stated purpose of the lab is to calculate the heat of vaporization for water. All right. Very simply. And the way you're going to do that is using the Clausius-Clapeyron equation. And last week in the Excel lab, you did kind of a dummy run of this to see what it looks like, or what it should look like anyway. So we're looking at this form of the Clausius-Clapeyron equation again. You're going to collect, what am I doing? You're going to collect multiple data points. So you don't want to use the 2-point version of the Clausius-Clapeyron equation. You're going to use this form. The natural log of the vapor pressure of a liquid. Let's try that again. Too far up out of shot. The natural log of the vapor pressure of a liquid is equal to negative delta H of vaporization divided by R times 1 over temperature plus some value A or B or whatever you want to call it. All right. And basically what this is telling us, as we said last week, is that if we plot the natural log of the vapor pressure on the y-axis and 1 over absolute temperature on the x-axis, we should get a straight line. All right, now, here's the problem we have in this lab. How do we do this? All right, we can't measure the vapor pressure of water directly. All right, and the reason for that is we can't pull a vacuum on the flask that we're using safely. All right, we have the ability to pull a vacuum, but and pull all the air out, but it's not safe with those little Erlenmeyer flasks. They can implode when you do that, and it's not good to be around something like that when it happens. So here's what we're going to do. When we take a pressure reading inside that flask, we're measuring what we're going to call the total pressure, right? And that total pressure is equal to the partial pressure of the air. Okay, we're treating air as a single ideal gas, plus whatever vapor pressure the water generates. All right, so what can we do with this? We can calculate the partial pressure or the vapor pressure of the water if we know what the partial pressure of the air is. All right, so we can just rearrange that equation. That's all we have to do. All right, it sounds really simple, and it is really simple. Here's the problem, though. How do we get this? That's what we have to think about. How are we going to get that partial pressure of the air? And the way we're going to do this is at the lowest temperature. We're going to say, all right, at temperature of less than or equal to 5 degrees, we're going to assume that there's no vapor pressure for the water. All right, that's what we're going to do. All right, and so once we've done that, what we can do then is this. We can say at that temperature, less than or equal to 5, then we can calculate the Gay-Lussac constant. And that's equal to the pressure of the air divided by the temperature in absolute or in kelvins. All right, that's what we're going to do. Now, here's a question for you. And this is something for you to think about, because what I'm going to ask you in the post lab is to comment on the flaws of this experiment. And there are some, okay? I deliberately designed it that way. But here's one question you want to ask yourselves. Is this a reasonable assumption? And why or why not? All right, you might be able to back it with some data if you go looking in the right places. All right, so basically what I want you to do is take the data that I send you, put it into the spreadsheet. You're going to have to do a data workup in the lab manual as well. Okay, basically what you're going to do is you're going to calculate this constant by hand with your lowest temperature pressure measurement, and then you're going to calculate the partial pressure of air at around 50 degrees. It doesn't have to be exactly 50 degrees. All right, just find the temperature where pressure was measured that's closest to 50 degrees, and that'll do you just fine. All right, then you're going to take the data, put it into the spreadsheet. The spreadsheet will generate all these calculations for you, so you don't have to do them by hand. And then you just make a plot of the last 2 columns from the spreadsheet, leaving out the first row, because the first row will have, if it's going to try to take a natural log of 0, and it doesn't like that. So you're going to just collect the data that has numbers associated with it and make the plot for that and see what it looks like. All right. Does it give you a reasonably close straight line? And then you're going to calculate the delta H of vaporization for water and include that in your data sheet. All right. That's it. It's pretty, again, it's a fairly simple lab. And if I had to choose a lab that I was not going to be here for, this would be the one, because it is so simple. All right. Does anybody have any questions on this before I go on? All right. Hopefully it's fairly straightforward. And again, if you have questions, what I'm going to do is I'm going to send each of you, again, an individual PDF file. All right. You definitely want to take a look at it. Once you've got that, you can start working on this. I'm going to stay on here for maybe a half hour, 45 minutes or so that if you have any questions or any issues with the data that you have, you can ask me about it directly. Then we'll end, And actually, you're free to go once you get the file. Okay, so once you do that, you can go if you want to, or you might want to stay on just in case you have any issues when you start working on things. All right, what I would recommend is you finish this morning. All right, no reason you can't. Get it all done. Probably finish by 11 o'clock easily. Okay, maybe even sooner than that. And then what I want you to do is, just go ahead and turn it in like you do a normal lab next week. All right. For this week's lab, if you want to and you happen to be on campus, feel free to go upstairs and you want to leave your lab manual with the lab coordinator. There's no problem with that. All right, you can do that if you like. All right. Okay.